Emergency position indicating radio beacon station is, according to Article 1.93 of the International Telecommunication Union's radio regulations, defined as a station in the mobile service the emissions of which are intended to facilitate search and rescue operations. In marine use, the terminology emergency position indicating radio beacon is used. General description: EPIRBs are tracking transmitters which aid in the detection and location of boats, aircraft, and people in distress. A PLB is a particular type of EPIRB that is typically smaller, has a shorter battery life, and unlike a proper EPIRB is registered to a person rather than a vessel. The terms ELB and ELT are used interchangeably with EPIRB only when used on aircraft. Strictly, they are radio beacons that interface with worldwide offered service of COSPAR-SAR-SAT, the International Satellite System for Search and Rescue. When manually activated or automatically activated upon immersion or impact, such beacons send out a distress signal. The signals are monitored worldwide and the location of the distress is detected by non-geostationary satellites, Doppler trilateration, and in more recent EPIRBs also by GPS. The basic purpose of a distress radio beacon is to help rescuers find survivors within the so-called Golden Day, during which the majority of survivors can usually be saved. Since the inception of COSPAR-SAR-SAT in 1982, distress radio beacons have assisted in the rescue of over 28,000 people in more than 7,000 distress situations. In 2010 alone, the system provided information which was used to rescue 2,388 persons in 641 distress situations. Most beacons are brightly colored and waterproof. EPIRBs and ELTs are larger and would fit in a cube about 30 centimeters on a side and weigh 2 to 5 kilograms. PLBs vary in size from cigarette packet to paperback book and weigh 200 grams to 1 kilogram. They can be purchased from marine suppliers, aircraft refitters, and hiking supply stores. The units have a useful life of 10 years, operate across a range of conditions -40 to 40 degrees Celsius, and transmit for 24 to 48 hours. The cost of radio beacons varies according to performance and specifications. Operation: the following is the process through which a transmission usually gets processed. The transmitter is activated, either automatically in a crash or after sinking, or manually by survivors of an emergency situation. At least one satellite picks up the beacon's transmission. The satellites transfer the beacon's signal to the respective ground control stations. The ground stations process the signals and forwards the data, including approximate location, to a national authority. The national authority forwards the data to a rescue authority. The rescue authority uses its own receiving equipment afterwards to locate the beacon and commence its own rescue or recovery operations. Once the satellite data is in, it takes less than a minute to forward the data to any signatory nation. There are several systems in use, with beacons of varying expense, different types of satellites, and varying performance. Note that carrying even the oldest systems provides an immense improvement in safety compared to not having a beacon. Activation: there are two ways to activate a beacon: manually or automatically. Automatic EPIRBs are water-activated, while automatic ELTs are impact-in monitors activated by G-force. Some EPIRBs also deploy. This means that they physically depart from the mounting bracket on the exterior of the vessel. For a marine EPIRB to begin transmitting a signal, it first needs to come out of its bracket. Deployment can happen either manually, where someone must physically remove it from its bracket, or automatically, where water pressure will cause a hydrostatic release unit to release the EPIRB from its bracket. If it does not come out of the bracket, it will not activate. There is a magnet in the bracket which operates a read safety switch in the EPIRB. This is to prevent accidental activation when the unit gets wet from rain or shipped seas. Once deployed, EPIRBs can be activated depending on the circumstances, either manually or automatically. All modern EPIRBs provide both methods of activation and deployment, and thus are labeled manual and automatic deployment and activation. Automatic Hydrostatic Release Unit. A hydrostatic release unit, or HRU, is a pressure-activated mechanism designed to automatically deploy when certain conditions are met. In the marine environment, this occurs when submerged to a maximum depth of 4 meters. The pressure of the water against a diaphragm within the sealed casing causes a plastic pin to be cut, thereby releasing the containment bracket casing, allowing the EPIRB to float free. Some common characteristics of HRUs are: water pressure sensitive at depths not to exceed 4 meters, less than 2 meters. Single use only, require replacement if activated, cannot be serviced, only replaced. Waterproof, sealed against moisture and tampering. Must be labeled with expiration date. Expiration date is 2 years from month of installation. Applies to unit and rod. Several regulations and technical specifications govern EPIRB hydrostatic release devices. ISO 15734. SOLAS 74.95, CFR Title 46 Volume 6 Section 160.062, USCG 160.162. Corrosion resistance test, temperature tests, submergence and manual release test, strength tests, technical tests on the membrane, performance test. Beacon operation GPS-based registered. The most modern 406 MHz beacons with GPS track with a precision of 100 meters in the 70% of the world closest to the equator, and send a serial number so the responsible authority can look up phone numbers to notify the registrator in 4 minutes. The GPS system permits stationary, wide-view geosynchronous communications satellites to enhance the Doppler position received by low Earth orbit satellites. EPIRB beacons with built-in GPS are usually called GPIRBs. The GPS position indicating radio beacon, a global position indicating radio beacon. However, rescue cannot begin until a Doppler track is available. The COSPASSARSAT specifications say that a beacon location is not considered resolved unless at least 2 Doppler tracks match, or a Doppler track confirms an encoded track. 1 or more GPS tracks are not sufficient. High precision registered. An intermediate technology 406 MHz beacon has worldwide coverage, locates within 2 kilometers, notifies kin and rescuers in 2 hours maximum, and has a serial number to look up phone numbers, etc. This can take up to 2 hours because it has to use moving weather satellites to locate the beacon. To help locate the beacon's frequency is controlled to 2 parts per billion, and its power is 5 watts. Both of the above types of beacons usually include an auxiliary 25 mW beacon at 121.5 MHz to guide rescue aircraft. Traditionally LT, unregistered. The oldest, cheapest beacons are aircraft emergency located transmitters that send an anonymous warble on the aviation band distress frequency at 121.5 MHz. The frequency is often routinely monitored by commercial aircraft, but has not been monitored by satellites since February 1, 2009. These distress signals could be detected detected by satellite over only 60% of the Earth, are required up to 6 hours for notification, located within 20 kilometers, were anonymous, and couldn't be located well because the frequency is only accurate to 50 parts per million and the signals were broadcast using only 75 to 100 milliwatts of power. Coverage was partial because the satellite had to be in view of both the beacon and a ground station at the same time. The satellites did not store and forward the beacon's position. Coverage in polar and south hemisphere areas was poor. False alarms were common, as the beacon transmitted on the aviation emergency frequency, and there is interference from other electronic and electrical systems. To reduce false alarms, a beacon was confirmed by a second satellite pass, which could easily slow confirmation of a case of distress to up to about 4 hours. Aircraft ELTs have been increasingly supplemented with ADS-B transmitters, which may be monitored by other aircraft to help prevent collisions. Location by Doppler. The COSPAR-SARSAT system was made possible by Doppler processing. Local unit terminals detecting non-geostationary satellites interpret the Doppler frequency shift heard by LEOSAR and MEOSAR satellites as they pass over a beacon transmitting at a fixed frequency. The interpretation determines both bearing and range. The range and bearing are measured from the rate of change of the heard frequency, which varies both according to the path of the satellite in space and the rotation of the Earth. This triangulates the position of the beacon. A faster change in the Doppler indicates that the beacon is closer to the satellite's orbit. If the beacon is moving toward or away from the satellite track due to the Earth's rotation, it is on one side or other of the satellite's path. Doppler shift is 0 at the closest point of approach between the beacon and the orbit. If the beacon's frequency is more precise, it can be located more precisely, saving search time. So modern 406 MHz beacons are accurate to 2 parts per billion, giving a search area of only 2 square km, compared to the older beacons accurate to 50 parts per million that had 200 square kilometers of search area. In order to increase the useful power and handle multiple simultaneous beacons, modern 406 MHz beacons transmit in bursts and remain silent for about 50 seconds. Russia developed the original system, and its success drove the desire to develop the improved 406 MHz system. The original system was a brilliant adaptation to the low-quality beacons, originally designed to aid air searches. It used just a simple, lightweight transponder on the satellite, with no digital recorders or other complexities. Ground stations listened to each satellite as long as it was above the horizon. Doppler shift was used to locate the beacon. Multiple beacons were separated when a computer program analyzed the signals with a fast Fourier transform. Also, 2 satellite passes per beacon were used. This eliminated false alarms by using 2 measurements to verify the beacon's location from 2 different bearings. This prevented false alarms from VHF channels that affected a single satellite. Regrettably, the second satellite pass almost doubled the average time before notification of the rescuing authority. However, the notification time was much less than a day. Satellites receivers are auxiliary systems mounted on several types of satellites. This substantially reduces the program's cost. The weather satellites that carry the SAR-SAT receivers are in all of yarn orbits, inclined at 99 degrees. The longest period that all satellites can be out of line of sight of a beacon is about 2 hours. The first satellite constellation was launched in the early 1970s by the Soviet Union, Canada, France and the United States. Some geosynchronous satellites have beacon receivers. Since the end of 2003, there are 4 such geostationary satellites that cover more than 80% of the surface of the Earth. As with all geosynchronous satellites, they are located above the equator. The GEOSAR satellites do not cover the polar caps. Since they see the Earth as a whole, they see the beacon immediately, but have no motion, and thus no Doppler frequency shift to locate it. However, if the beacon transmits GPS data, the geosynchronous satellites give nearly instantaneous response. Search and rescue response. Emergency beacons operating on 406 MHz transmit a unique 15, 22, or 30-character serial number called a hex code. When the beacon is purchased, the hex code should be registered with the relevant national authority. Registration provides search and rescue agencies with crucial information such as phone numbers to call, a description of the vessel, aircraft, vehicle, or person, the home port of a vessel or aircraft, any additional information that may be useful to SAR agencies. Registration information allows SAR agencies to start a rescue more quickly. For example, if a shipboard telephone number listed in the registration is unreachable, it could be assumed that a real distress event is occurring. Conversely, the information provides a quick and easy way from the SAR agencies to check and eliminate false alarms. An unregistered 406 beacon still carries some information, such as the manufacturer and serial number of the beacon, and in some cases, an MMSI or aircraft tail number ICAO 24-bit address. Despite the clear benefits of registration, an unregistered 406 beacon is very substantially better than a 121.5 243.0 beacon. This is because the hex code received from a 406 beacon confirms the authenticity of the signal as a real SAR alert. Beacons operating on 121.5 and 243.0 MHz only simply transmit an anonymous siren tone, and thus carry no information to SAR agencies. Such beacons now rely solely on the terrestrial or aeronautical monitoring of the frequency. In the UK, the Distress and Diversion Cell of the Royal Air Force provides continuous monitoring of 121.5 and 243.0 MHz, with auto-triangulation from a network of terrestrial receivers on both frequencies. In Canada, only air traffic service stations monitor 121.5 MHz during operating hours. Overflying commercial or private aircraft monitor 121.5 MHz only if equipped with a suitable receiver, and if time courtesy permits, monitoring 121.5 MHz is not mandatory. SAR authorities have no way of knowing whether a 121.5 243.0 MHz signal is actually a SAR signal until they physically deploy to the location and home in on the source of the transmission. Since SAR resources are scarce, most countries do not deploy the most useful SAR homing assets until ambiguity has been resolved. Operational testing. According to the U.S. Federal Aviation Administration, ground testing of A, B, and S-type ELTs is to be done within the first 5 minutes of each hour. Testing is restricted to 3 audio sweeps. Type 1 and 2 devices have a self-test function and must not be activated except in an actual emergency. The United States Coast Guard webpage for EPIRB states, "You may be fined for false activation of an unregistered EPIRB." The U.S. Coast Guard routinely refers cases involving the non-distress activation of an EPIRB to the Federal Communications Commission. The FCC will prosecute cases based upon evidence provided by the Coast Guard, and will issue warning letters and notices of apparent liability for fines up to $10,000. Beacon modes. The most important aspect of a beaconing classification is the mode of transmission. There are two valid transmission modes, digital and analog, where digital usually has a longer range. Analog is more reliable. Analog beacons are useful to search parties and SAR aircraft, though they are no longer monitored by satellite. Digital mode, 406 MHz beacons. 406 MHz beacons transmit bursts of digital information to orbiting satellites, and may also contain a small integrated analog homing beacon. They can be uniquely identified. Advanced beacons encode a GPS-GLONASS position into the signal. All beacons are located by Doppler triangulation to confirm the location. The digital data identifies the registered user. A phone call by authorities to the registered phone number often eliminates false alarms. If there is a problem, the beacon location data guides search and rescue efforts. No beacon is ignored. Anonymous beacons are confirmed by two Doppler tracks before beginning beacon location efforts. The distress message transmitted by a 406 beacon contains the information such as which country the beacon originates from, a unique 15-digit hexadecimal beacon identification code, the encoded identification of the vessel or aircraft in distress, either as an MMSI value or, as in the case of an ELT, either the aircraft's registration or its ICAO 24-bit address. When equipped, a GPS position, whether or not the beacon contains a 121.5 MHz homing transmitter. The digital distress message generated by the beacon varies according to the above factors and is encoded in 30 hexadecimal characters. The unique 15-character digital identity is hard-coded in the firmware of the beacon. The 406.025 MHz carrier signal is modulated plus or minus 1.1 radians with the data encoded using Manchester encoding, which ensures a net zero phase shift aiding Doppler location. 406 MHz beacon facts and transmission schedule. 406 MHz beacons transmit for a quarter of a second immediately when turned on, and then transmit a digital burst once every 50 seconds thereafter. Both GEOSAR and LEOSAR satellites monitor these signals. The repetition period shall not be so stable that any two transmitters appear to be synchronized closer than a few seconds over a 5-minute period. The intent is that no two beacons will have all of the bursts coincident. The period shall be randomized around a mean value of 50 seconds, so that time intervals between transmission are randomly distributed on the interval 47.5 to 52.5 seconds. Preliminary specification for second-generation beacons. From beacon activation, a total of initial transmissions shall be made separated by fixed intervals. The first transmission shall commence within seconds of beacon activation. Transmissions shall then occur at nominally second intervals until minutes after beacon activation. The repetition period between the start of two successive transmissions shall be randomized around the stated nominal value, so that intervals between successive transmissions are randomly distributed over plus or minus seconds. Subsequent transmissions. 406 MHz beacons will be the only beacons compatible with the MEOSAR system. 406 MHz beacons must be registered. Hex codes. Example hex codes look like the following: 90127B92922BCO22FF103504422535A bit telling whether the message is short or long format. A country code, which lets the worldwide COSPAS/SARSAT Central Authority identify the national authority responsible for the beacon. Embedded 15 hex ID. A 15 hex transmitted distress message, for example, 2024F72524FFBFF. The hex ID is printed or stamped on the outside of the beacon and is hard-coded into its firmware. The 15 hex ID can only be reprogrammed by certified distress radio beacon technicians. The national authority uses this number to look up phone numbers and other contact information for the beacon. This is crucial to handle the large number of false alarms generated by beacons. A location protocol number and type of location protocol, EPIRB or MMSR, as well as all the data fields of that location protocol. If the beacon is equipped with GPS GLONASS, a rough latitude and longitude giving the beacon's current position. In some aircraft beacons, this data is taken from the aircraft's navigation system. When a beacon is sold to another country, the purchaser is responsible for having the beacon reprogrammed with a new country code and to register it with his per nation's beacon registry, and the seller is responsible to deregister the deprecated beacon ID with his per national beacon registry. One can use the beacon decoder web page at COSPAS/SARSAT to extract the 15 hex ID from the 30 hex distress message. AISR. These devices are similar to traditional SAR radar transponders, which additionally include a GPS receiver and a transmitter on VHF AIS channels, so they show up on ship AIS receivers. They are lightweight and can be used to equip inflatable life rafts. Analog mode. All other beacons a simple analog SAR and tone is transmitted continuously until the battery dies. In the case of 121.5 MHz beacons, the frequency is known in aviation as the VHF guard emergency frequency, and all U.S. civilian pilots are required by FAA policy to monitor this frequency when it is possible to do so. The frequency can be used by automatic direction finder radio navigation equipment, which is being phased out in favor of VOR and GPS but is still found on many aircraft. The COSPAS/SARSAT system detected this type of beacon prior to the 1st of February 2009 when a LEO-SAR satellite was in view of both the beacon and a LEO-LUT satellite detection of 121.5 MHz beacons ceased on the 1st of February 2009. Frequency. Distress beacons transmit distress signals on the following key frequencies. The frequency used distinguishes the capabilities of the beacon. A recognized beacon can operate on one of the three COSPAS/SARSAT satellite-compatible frequencies. In the past, other frequencies were also used as a part of the search and rescue system. COSPAS/SARSAT compatible beacon frequencies see above for transmission schedule. 406 MHz UHF carrier signal at 406.025 to 406.076 MHz plus or minus 0.005 MHz. Channel frequency CH1 at 406.022 MHz. CH2B 406.025 MHz. CH3C 406.028 MHz. CH4D 406.031 MHz. CH5E 406.034 MHz. CH6F 406.037 MHz. CH7G 406.040 MHz. CH8H 406.043 MHz, CH9I 406.046 MHz, CH10J 406.049 MHz, CH11K 406.052 MHz, CH12L 406.055 MHz, CH13M 406.058 MHz, CH14N 406.061 MHz, CH15O 406.064 MHz, CH16P 406.067 MHz, CH17Q 406.070 MHz, CH18R 406.073 MHz, CH19S 406.076 MHz. COS are at incompatible beacon frequencies. Marine VHF radio channels 15/16. These channels are used only on the obsolete Class C EPIRBs. The obsolete Inmarsat beacons transmitted to Inmarsat satellites on 1646 MHz UHF. 121.5 MHz VHF plus or minus 6 kHz, 243.0 MHz UHF plus or minus 12 kHz.